So this is one way to define
you
it.
don't mean this. You mean that the difference from
I mean this.
from a half. Yeah.
So this is a probability. And this is modulo 2. So we choose an element of this set uniformly at random. We take the XOR of the bits. This is how I define it. You can. We take the XOR of the bits in the set T, which is non-empty, and this random variable is equal to 1 with probability roughly 1/2 and 0 with probability roughly 1/2. And so this is a definition of an epsilon-biased set. So I think, so they are related, such sets are related to many pseudo-random objects. So they are related to expanders. Such sets have, just by definition, small Fourier coefficients, in some sense.
Over F2 to them.
Yes. And they are related to coding. So this set is also a code with some parameters. So they are related to many things. And in this talk, I will try to yes.
It's general.
Yeah, they are related to code.
Is there anything about the size? Because if you take the whole space, then that's trivial.
So yeah, what we will want to do is for a fixed epsilon n to find the smallest, the smallest x that we can, the smallest set, smallest support size. So.
Let me add just one more thing.
Yes.
It's related to it. It's the same thing, but that Sergey in his lecture called this parameterization of coherence.
Yes. So this is. All right. Okay. So, okay. Before giving specific construction, so the size of X is, so there is a lower bound on the size of such a set X, and this is either so the size of such a set is always at least this number or this number, the minimum between the two. So this was proven by McAleese, I don't remember, McAleese, Rodmick, Ramsey, and Welsh, and by Noga Alon, and also in a paper of Noga, Oded, Hastad, and Peralta. And maybe in more places, I don't know.
Now, can you write the family name because we're not recording?
Yeah. So this is Mac. I hope I'm not writing it McAleese.
This first is a famous so-called linear programming law bound. It actually proves something stronger. It just.
This is a special case. And last time there was this trick of taking a matrix and raising it to some power, and this will give some lower bound on the rank. So this is the way Noga Alon proved this lower bound. Okay, so this is in terms of lower bound. A random set of size is epsilon bias. So,
Without problem.
yes.
So there is a difference between the lower bound.
Yeah, there is this thing.
Yeah, nobody knows. That's a big question in coding. The random set construction is also for the coding. It can be achieved greedily, not just by random. It's Gilbert-Bosch-Amor bound, and nobody knows whether it's the best.
So this is in terms of, so we know that there exists good epsilon-biased set of almost optimal size. So we still have some gap in our knowledge, but if we ignore logarithmic factors, then they are optimal. And the big question in this is to achieve this with an explicit construction. So I will now give a survey of what is known, and then we'll explain, give the constructions explicitly. So I think the first ones to show something was Naor and Naor. This is true. And they proved something of the form. So now explicit. So everything here will be explicit constructions. So they defined and they constructed X of size n over poly epsilon. So they defined it and constructed such a set. Then I think, I'm not sure about the historical order, but this paper, they constructed a set size n over epsilon squared. And then there is Alon is Noga Alon. A is Noga Alon. Bruck, Naor, and Roth. So these names are the ones that appear here. This is Noga Alon. They constructed a set size roughly n over, yes, this is n over epsilon cubed. And lastly, so I will try to fit it here. Ben-Aroya and Ta-Shma constructed a set of size n over epsilon squared to the 5/4 for epsilon smaller than 1 over the square root of n. So these are the best construction that we know today. And So I will try to make some drawing to explain these parameters. So just for example, let's see what happens when epsilon is 1 over n. So the optimal construction is of size roughly n to the power of 3. So this construction is better than this, so I'll focus on this. This construction is size n to the 4. The other one is also size n to the 4. And this one is of size n to the 15 over 16, I think, which is better than
15 over 4.
15 over 4, yes. Which is better than this and this, but is not as good as the optimal one for this parameter. So this is just an example. And in general, how does it look like? There is, if this is epsilon, then there is 1 over square root of n and 1 over n to the 1.5. In this region, this goes like n over epsilon to the 3. In this region, it goes n over epsilon squared to the 5 over 4, and in this, n over epsilon squared. So this is how it looks like. And below all of this, there is some lower bound, which is n over epsilon squared. So this is the way the world looks like as we know it today. So this is clear?
It's clear. Probably the axis should be called 1 over epsilon if you want this numbers to be bigger on the right. And to the 1.5 bigger than square root n. It doesn't matter.
I think it makes sense, but okay. Yes. Okay. So, what?
Epsilon becomes smaller when you go to the right.
Yeah, so the axis is really 1 over epsilon.
It's the inverse.
Yes.
The axis.
So this is smaller than this, yes.
Yeah. Why not?
Okay. So what I will try to do today is explain. I'll try to explain this first, this construction, and there will be actually the zero construction, which is what Alexandra said. And then I will show almost this with some polylog difference because it's simpler. And then I will explain this, how to do this. And hopefully I will give some reasonable explanation about algebraic geometric codes, not in detail, but in high level, like what's going on there. Okay, so I want to start with the simplest thing is epsilon equal to 0. When epsilon is 0, then we have a lower bound of 2 to the n. So we can't do much. And what we will do, one way to do this is if we have this set T, then we will think of T as some G in F2 to the n. This is one way to define it. So we will think of a non-empty set as an element in here, which is non-zero, if this is non-empty. And what we will do is we'll take the first bit of x times g, where x is everything. So this will be our construction.
You really want to define,
So
it's a little different than your definition, but
What's the connection between?
yeah, what's the connection?
Yeah, so we'll take. Yeah, so this in the definition there it will be. So each x will be uniform in 0, 1. Each coordinate will just be uniform, and we will take. So if we take x to be all of this, this just settles with this definition.
The point is that the exclusive of these bits of xi can be viewed as a result of just a multiplication in the big field.
Yes. So this is a field element in a big field. This is also a field element. The product is also a field element. Product as field elements. No, as field elements. It's some product.
But multiplication is a bilinear operation, so it's really a...
So yeah, this is linear in G. This is the important point. Okay, and this in the coding theory language, this is the Hadamard code. Okay. The second construction will use this somewhere inside, but it will be, so I think you said this is Alon and Kushilevitz or Mansour?
Alon and Mansour.
Alon and Mansour. So, how do you do this? What they suggested is we take a field f of size roughly n over epsilon, and we will choose the set X not explicitly but sort of implicitly. How will we do it? We will choose Y and Z in this set, in this field, and then Xi will be the first bit of Z times Y to the power of I. And this is in the field F.
F will have characteristics.
Yeah, so we can either take some character of the field, or it's like, yeah, if F is of characteristic 2, we can really take the first bit. Otherwise, we can make it some character.
You write trace instead of first bit.
You can take any character, yes. But
Shorter to write.
I don't understand what you mean by first bit. I'm sorry.
so,
In the top part, in the zero construction, what is first bit of x?
So why don't you write the trace of...
If the field is characteristic too, then
Yeah.
it's just a
I
trace.
mean, what are you taking? Like, first bit of x times z equals what?
this is our random bit. So,
Yeah, but you have to say how.
yeah, so this is a definition of the set. This is a definition of the set.
Okay.
So this is like some way I think of this. Maybe it's not natural to you, but this is just the definition of the set. If you take this set, it will work. So this is just take a uniform element here, take the XOR of the bits in any subset.
I understand. Just
Yes.
the sentence first bit of x times z, I don't connect it to the left side of the sentence.
Yeah, it's
and the
very
right
hard
side
to
of the
connect it, but
For me, it's
I
very.
don't know what it means.
the,
Like, why is it-
the exclusive OR of the bits in T of x of a particular vector x, yes, the exclusive OR happens to be the first bit of the result of multiplying x as a number in this field with some fixed number related to T. It's called GT or something like that.
What is G? Is
Can you
the
write
binary,
x times
is the
G?
binary decomposition of G equal to 1, 1 when it's
There is a one-to-one correspondence between non-empty subsets T and elements of the field.
Yes.
G, maybe you should call it G sub T or something.
That is clear. I just don't
No, but it's not clear.
Oh, sorry.
Just
What is the pointwise multiplication? I don't understand. Like,
it's not pointwise.
But
This is a field, so I'll try to explain it better. So what I wrote here is that this random variable, which we want to say is close to being uniform, in this, if we choose this set, then this random variable is equal to the first bit of this field element.
why?
So yes, it doesn't matter. Any bit,
No,
let's
but
say on the
call
left.
G, I mean, it's not clear what's the correspondence between G and T. This is, yeah, G and the, no, this is,
Filling the whole space is a big field, F to the n, field of size to the
I
n.
understand
So
that.
every linear mapping from this big field to a small field F2 can be realized as the first bit of a product with some element. It's a
Okay.
theorem.
I didn't realize that you're mapping to F2.
Yeah, it's a big field and
I
a
have
small
no idea
field.
where this connects to everything. Fine.
So yeah, yeah. So is it clear? So here I will also define it in this way. This is sort of an implicit definition of the set. So here it's actually explicit. So I'll try to make it. So xi will be the first bit of this number. And this field, let's say, is of size f2 to the k. Well, k is roughly log n over epsilon. So what does this mean? For every two elements here, we define a string of length n. This will give us a definition of a set X. The set X is all the x's that can be obtained by this process. So what is the size of the set X? It will be the size of f squared. Is it clear? For every y and z in F, there are f squared such elements. We define one element in X. So the size of X will be f squared. So yeah. What? So let's say that it doesn't. So let's say that it's only at most f squared, but I think they will be different.
Define for pairs.
What?
Define for pairs. Every pair.
Oh, what Alexandra asked, as far as I understand, is this map one-to-one? Like,
Oh.
but let's just ignore this. It's not. So this is a construction, and the size of this construction is n over epsilon squared up to constant factors. Okay, so it's clear what is the definition of the set X. So, okay, and now why does this construction work? The analysis has two steps. And I will try to explain why it's natural to have two steps. So what is the sum? So we want to show that this is 0 and 1 with probability 1/2. So we will show that this expectation of -1 to this number is small. If this expectation is small, then this will be a biased, a not biased bit.
expectation over y and z.
Yes. So this is over x in x, which actually means over y and z in f squared. So what is this thing? So this, I will denote it like generally as the expectation over y and z of some, I will write something. So minus 1 to the power of this thing is some additive character of this field. And the element xi is the additive character in this position. So the first bit of this thing is xi. So psi of this thing will correspond to the first bit. So is it clear? So I just rewrote it and replaced xi by our construction. So v can go outside because it's independent of I, and here we have some powers of I. And now what is this equal to? So there are two situations. One situation is when y vanishes
Don't you want
here.
to write another step where you call this sum f of y for some polynomial?
And we can denote this as g of y, when g is a non-zero polynomial. So we can write it also as sum c g of y. Okay, so this is just, I call this thing g of y. And now there are two cases. The first case is where g of y is 0. When g of y is 0, then this whole thing is 1. So this is equal to the probability over y that g of y is 0. And now we have the complement thing. So we have the expectation over y such that g of y is non-zero. And then we have the expectation over x, psi of x, sorry, z, g of y.
That's an upper bound.
No, this is inequality.
No, because then you have to take the probability, add the expectation.
Yeah.
and this,
So,
yeah.
we can, never mind. So, and now this quantity, this is a polynomial of degree n, because in one variable, and it takes values in the field of size n over epsilon. So this is at most n over epsilon, roughly. So there is some. And this quantity, now g of y is non-zero. So a character over the whole field is always 0. So this is equal to 0, and this is at most epsilon. So, okay, so is it what I wrote sort of clear?
So the second 0 is due to the fact that you average over z?
Yes.
The average over z is always. Yeah. So, okay, what happened here? So this sort of another way to view the same construction is in 2 steps. So in the coding version of this construction, it has 2 steps. First, we take Reed-Solomon. And then we concatenate it with Hadamard. Why am I calling this? Why do I call it like this? So if we took only this, just y to the power of I, then it will be exactly Reed-Solomon encoding, and the fact that this will be.
It's not clear what you are encoding. I mean, in this language, you are encoding the subset t by polynomial.
Yes.
Yeah. So what is being encoded, if you call it encoding, is the subset t is encoded by the polynomial sum right to the I over the elements in I and D.
So, is it? Yeah, okay. And in the second step, we multiply by a uniform field element, which is exactly what we did in the first construction, to get zero error. And this is exactly this 0. So this is, we use this and Reed-Solomon to get a construction that works for every epsilon. And it's pretty good. Okay, now I will want to explain the second construction.
So you could also try to just use Reed-Solomon and take a slightly bigger field and to use Dale. So it's something that
There's no advantage in taking a bigger.
no, you don't use Dale.
Yeah.
So you take a bigger field and the degree of
Therefore, what
probability
is the range of?
no Z, just Y to the I.
I think that this will be worse in terms of
Of
parameters.
course.
Yes.
There is a construction which is as well in AGHP. One of the constructions does it just a similar way,
Yes.
but I don't think it will show it.
Yeah, the reason I showed this is I think that if you see this, then this 2, at least with the tilde, is clearly, not clear, is like simple alternation on this. So where is the part that we lose here? Sort of the part that we lost is here. Here we could have paid epsilon, but we paid 0, we didn't pay at all, which could be sort of lossy. And so this is one point. A second point, which is a very good thing about the first construction, is that it's optimal as a function of epsilon. So this construction is optimal in epsilon. So this is another good point about this construction. And now that I made these 2 comments, then I think it's sort of maybe simple to see what we should do. So I will try to, can you see this color?
I don't know if it's so good for the camera.
Yellow.
Yeah.
So I'll try to go over this and explain how to do 2. So again, we lost here the 0. And how can we not lose it? Sort of the way we got 0 is we chose Z in the field. Another way to choose Z is in an epsilon-biased for F, for log F bits. So now, after we did this step, we got a non-zero element in the field F.
Epsilon-biased for what?
For log F.
Log F bits.
Log F
N
bits.
equals log F.
Yes. So intuitively, after we did this, we lost epsilon, and then we can sort of condition on the fact that this is non-zero. Now, if we use an epsilon bias on G of Y, so instead of taking all Z here, we take Z that comes from an epsilon biased set, this quantity will be, instead of 0, at most epsilon. So if we take the construction of step 1 for log F bits, so now in the second construction, we will take Z to be in an epsilon biased of log F this is just a notation to denote that we choose z to be in the epsilon biased of log f, and we take it according to the first construction on a smaller set. So like z will actually be the sum, z in the ith position will be w times v to the power of I when w and v are inside a smaller field.
But this is not the parameter of the force.
So it is the parameters I promised. Why? Because log of the size of the field is negligible. It's log n and log of 1 over epsilon, so we can ignore this. And the dependency on epsilon is optimal. It's 1 over epsilon squared.
What do you mean? Is this optic?
No, he said that he will put 2 tilde. The tilde is another polylog factor. Yeah.
So I will write exactly.
So the n over epsilon cube is not n over
Yeah,
epsilon cube,
but-
it's O tilde.
Yes, this is the tilde.
This will be O tilde.
Yes.
You can put tilde also there. But
Yeah,
it's-
Yeah. So I will say how to get this as well, but I will not give it explicitly. I will mention how to get
This
this.
is because, could you say again, so this is just n over epsilon cube, no extra logarithms?
There is a construction of this.
Yes.
There is a construction. What we showed here,
So it is just n over epsilon cube, yes?
so
No logarithm for anything.
in their construction, yes, and I will say how to get it, but not as explicitly as here. So what we just showed, is a set of size log n over epsilon squared times n times epsilon to the power of 3. This is what we showed now.
So to get rid of the logarithms, you keep iterating the same construction with itself? Or?
No, it's a different.
But, yeah. So this is clear?
So what I try to explain now is the construction of this. So maybe I should write it like. So this is the z part, and this is the y part. And again, in the coding theory language, which is, we did y is the same, so it's Reed-Solomon. And then we concatenate it, not with Hadamard, but with a smaller epsilon bias. Okay. So now, before I'll explain the third construction, I want to discuss this a bit in higher level, and to say how, after this high level, how we sort of get this construction without the logarithmic factors missing. You can try. I don't think it will give you anything better than the logarithmic factors. Like,
To take a slightly smaller field.
I don't know.
To try
Yeah.
to use.
Yes, but I don't know how to do
So
it.
a random polynomial will not have you.
Yes. Yes. Okay. So a higher level description of these two constructions in this language is we first, in the first construction, we took a Reed-Solomon of distance 1 minus epsilon. So the probability, the minimal number of non-zero entries in this encoding is epsilon. Of zero entries is epsilon. So the number of zeros in this encoding, the number of y's for which this is 0 is at most epsilon. So the distance is at least 1 minus epsilon. And then we concatenate it with Hadamard, which is a code of distance exactly 1/2. In the second construction, we took the same thing, y minus epsilon, but we concatenated with 1 with half minus epsilon. So we increased the minimal distance a bit, and this is still good for us. So I'm going to say one way to view this. So in the first step, in this step, we chose L1 to LK linear maps from 0, 1 to the n to some field F. So, okay, I will write it, and then, so for every non-zero, non-empty set T, the probability of Li of GT B0 is at most epsilon. So, and this K was n over epsilon in our construction. We had n over epsilon linear maps. What are these linear maps? They were Li was of T was sum over I in T, y to the I. This is L of y.
The evaluation.
Yes. So in a more abstract way, we defined K linear maps from 0, 1 to the n to some field F with this property. And the reason here we paid again the size of F, to get exactly rate 1/2, to get 0 error, so here we must use, so the construction here will be always of size K to the size of F if we concatenate with Hadamard. So we take a linear map and then we multiply by a random field element. So this is the size of the construction in the first case, in this case.
Yeah, why don't you write 1 to the left of it and 2?
Yes. And here we got K times log the size of F over epsilon squared. So these were the two constructions that we saw. And in the second construction, the size of the field is not very important because it's, there is a log. But in the first construction, the size of the field is very important. This is why we lose so much. And we can ask ourselves, what is the smallest field for which we can have this? If we can make the field smaller, we would pay less. So because the probability is at most epsilon, the size of the field must be at least 1 over epsilon. This is so this is not very hard to see. There are, like, we want things to happen with small probability, that we need a large sample space. Otherwise, if we take a random element here, so a random element here, this will happen with probability 1 over the size of f. So this is one thing. But if we had this construction, if we could achieve a field of size 1 over epsilon, roughly, then we get a construction of size n over epsilon squared, which is optimal. So we could hope to get such a thing. And as far as my calculations tell me, and I'm not sure that they are correct, we can a random set of n over epsilon such mappings, and a field of this size will be good. So we can achieve this with a random set. And now we want to achieve this with an explicit set. And this is exactly what algebraic geometric codes give us. They give us the ability to make the field smaller. So in Reed-Solomon, we need to take a large field. In algebraic geometric code, we can take smaller fields. So GOPA codes, or algebraic geometric codes, give a field of size 1 over epsilon squared. And then the construction is of size n over epsilon to the power of 3. We take this code, we pay, so the field is of this size, and k is n over epsilon. So this is what algebraic geometric codes give us. And then we get this result without the logarithmic factors.
That's not how they did it.
Yes, they use expanders in some way. And I will try to explain something about these codes, but not like, I will not explain how to construct it explicitly, because this is a separate talk. I can give some intuitions, and I don't understand exactly what's going on there as well. Okay. Yeah, and also the smallest size of such a field is also a big open question. Like we now noted that if we can make this field smaller, we get automatically epsilon-biased sets which are better. But this is like even maybe a more basic problem, trying to find such linear maps with smaller fields. So
it's not equivalent to epsilon-bias?
I don't think so, but maybe. So this is about being 1 minus epsilon distance, and epsilon bias is half plus minus epsilon. So it's like half minus epsilon. So it's like okay. So maybe now it's a good point to stop. And after the break, I will explain this construction and some things about algebraic geometric codes. To explain this construction. So the first construction, another comment I wanted to make is that this is optimal on n, which is also good. In n, which is also nice. Okay, so in the first construction, we used univariate polynomials. So we used the fact that a polynomial in one variable does not have too many zeros. Another, like if we can use one, why not bivariate polynomials. And the answer to this is that these bivariate polynomials in general gives worse parameters in this. Worst parameters.
T instead of T.
Yes. Worse parameters.
Even worse than this.
Yes. So I think that Gopa was the first one to think about it, is that bivariate polynomials don't really give worse parameters, but we need to do something. So what did we do in one? We interpret the set as some non-zero polynomial g of t, and then evaluated on all the field. And in the first step, this was univariate. And in the bivariate case, we can try to do the same thing. We interpret, so this is, we can interpret t as some non in two variables. And we can evaluate on f squared. So this is some way to do it. And this way of thinking actually gives worse parameters. But what Gopa thought of is that this is a very wasteful way to do this in some scenarios. So Gopa, which started the whole algebraic-geometric code thing, in some sense tells us that we should de-randomize f squared, not choose all points in f squared, but choose some points in f squared. And the way he suggested to do it is, instead of taking all points in f squared, is to evaluate, this is Gopa, evaluate on some variety in f squared. For example, v will be all the zeros of a polynomial, and p is irreducible.
Yeah, but you should say AB because the bivariate.
Yeah, so it's like a so this is the high-level idea. Not
Bivariate, yeah. In this, you can do more, but in this setting it will
Yes.
be
Is
bivariate.
P once and
yeah, yes.
You identify two polynomials if they agree on this
You will see.
sort of points.
Well,
It's
the
not,
filters will be
enough.
up to the GS.
Oh,
It's not to distinguish between all low-degree bivariate polynomials. You need the whole field.
yeah, I didn't say exactly how to do it, but
The degree will be bound.
you either bound the degree or look on a certain subspace of polynomials.
Yeah, I mean, you
But-
can't. You have to look at polynomials that if they agree on this curve, then you have to.
Yeah,
take
you,
it
you,
as the same.
yeah, this has
Oh.
to happen. This will happen.
Yeah,
Yeah.
but this is like the high-level idea, and maybe what Zeev said can also be mentioned in this high-level context, is that now we can sort of, in some cases, actually we will do this, but in some cases we will not want all polynomials up to a certain degree, because this will have too little information about all these polynomials. But instead we will choose this correspondence in a smarter way. We will take some subspace of polynomials with some properties. So this is the high-level idea. And now, so this was just some abstract discussion. Now let's see exactly what Ben-Aroya and Ta-Shma suggest to do. And I will not discuss this point of view. I will give like an explicit description of what they suggested, and I will follow. They also wrote it. I didn't come with this. So now we will take T to be GT, and GT will be so we'll interpret a subset, T, a non-empty subset, with a non-zero polynomial in this span. So we will have polynomials in two variables, and the individual degrees are at most d. And the way we do it is that sort of the coefficient of ai b to the j is t in the position ij. And so this is
So what is T?
T is a subset or a vector. So here,
You can think of T as a root n by root n matrix instead of a vector of size n.
so is it clear how we interpret so we think of this subset as being indexed by pairs of elements at most d. So this tells us that n is roughly d squared. And now we put here 1 or 0 in front of this monomial if this thing is in T, in a big universe. So this is similar to what we did before. Before we took polynomials of degree at most n in one variable. Here we take polynomials of degree at most square root of n in two variables. So this was the first step. And the second step is to define this variety, following GOPA idea. So the variety will be the variety that
Well, we call them also AB now.
will be this variety. And now the only thing is to define this. And I think there are a few ways to choose these polynomials, and these ways come from some intuitions in algebraic geometry. But we will choose a specific polynomial, which is trace of A plus norm of B. This is just notation. This actually means A to the power of P plus A plus B to the power of P plus 1. And we will fix the field to be Fp squared. So this is a polynomial in two variables. It's defined in a very simple way. And it's important that we think of all of this as being in a field of size p squared.
The output of the polynomial is in the subfield Fp.
Yeah, so why the reason we choose this choice, so this also makes this definition exactly the trace, and this is the norm, is that this P has a few good properties for us. First, P is irreducible. And I will not prove it. It's this one way to do it, which is what they do, is use Eisenstein criterion for showing that a polynomial is irreducible.
Absolutely irreducible?
In any extension, I think it is.
Yes,
Yes. And the second property, which is also very important for, so
Yeah, you don't need absolutely for this argument.
so he doesn't usually use that.
another thing is, so I will ignore this +1 for the calculations. It's just
Maybe you make one of the piece smaller.
so, so this is roughly true. So never mind.
The
Ah,
polynomial is the prime.
yes, you're right. So let's. Sorry. And the third property, which will be very important for us, is the following. The trace is a map from fp squared to fp. It's a linear map from fp squared to fp. This is one property. And
Linear? Trace?
it's linear in...
Trace, but not the norm.
No, the norm is not linear. Yeah, I said, yeah. And this map is also from fp squared to fp. And if you count roots, so the statement is that I want to say is that the size of V is we can choose B to be whatever we want. This is P squared. And after we chose B, then the number of A's that go to this specific N of B is P. So the number of roots is P to the power of 3. So these are the properties that we are going to use. Maybe I write it like this.
More than you expect in general.
Many things.
That's where you gain.
Yes. Okay, now that we have this, then, so we chose how to interpret a set as a polynomial, and we defined the places where we evaluate. So this defines the epsilon-biased set. And now we want to show, so we want,
No,
so
this defines
this defines the first step of the construction. So,
What's the relation between N and P?
so I will show it in a second. So this gave us, so what is so the size of the epsilon bias set is the size of V so far, so it's the size of X, this is capital X, will be P to the power of 3. This is the first step, evaluating on all these points. And the second step, we will multiply by a random field element. Again, concatenate with the Hadamard code. And the size of the field is P squared, so we will pay another P squared, and in total, it will be P to the power of 5. Okay, so this is the size of the construction. This is the variety, and this is a random field element. And like, know that the original thing will take, like the natural thing, if we don't, not natural, the simplest thing is take V to be everything, and then it will be P to the power of 6. So we save one in the power of this, in the size of this set.
Can you imagine having the inner
So,
somehow not.
so this is one choice. Another choice is to concatenate with a different, with an epsilon-biased set. This will give us a size p to the 3 over epsilon squared. And for these purposes, this will be a worst construction because we will have this requirement on epsilon. So the smaller the epsilon, this is worse than 1 over p squared. So we either pay p squared of 1 over epsilon squared, and it will be better to do this than this, but maybe other things can work. Like, so this is the way they define it. And now we have to define what is d and p as a function of n and epsilon. So let's see how this happens. So the second part of the construction adds no error because it's a Hadamard encoding. So we just need to estimate the probability of getting a non-zero field element, a non-zero field element in fp squared in the first step. So what is the probability over a and b in V that gt of a and b is 0? We want to show that this probability is small. This is equal to the size of the variety of G intersection the size of the variety of Q over the size of Q. And this denotes this set, so this is V of Q. And we can do the same for V of G. So this is just like equality. And now is the place where we need to argue something. So this polynomial is a polynomial of total degree at most 2D. This is an irreducible polynomial of degree p. So I want to say that this thing is at most 2D times p plus 1, and over p to the power of 3. So this I just copied. And why this is at most 2D to the power of p plus 1? This is what is called Bezout theorem. So it says that if two polynomials of degree d and p roughly have more than these many roots, then they have a common factor. But since this polynomial is irreducible and this is of lower degree, they cannot have a common factor. So the number of roots here is at most this much.
Where do you use the fact that you took the norm? I mean, you could have taken any function of p.
You need to prove that it's irreducible.
Irreducible, and it has to map to the small.
Yes. For example, taking the trace of b is not good, for example. Yes, it's not irreducible. And what we want to happen is this be at most epsilon.
This has to be at least epsilon. Epsilon has to be smaller than, I mean, that's the way we bound it.
No. No, this is,
Oh, sorry, yeah, this way, yeah.
we want, so okay, this is the error in the first step of the construction, and we want this error to be at most epsilon. So now I will ignore this p plus 1. So what we want is d to be at most.
Ignore the one.
Yes. So this is one condition. Another condition that we have from before is d roughly n to the 1/2. So we choose d to be roughly n to the 1/2. And this tells us that p should be n to the 1/2 over epsilon to the 1/2. No. Which is n to the 1 over 4 over epsilon squared. Epsilon 1/2. No, you're confusing me. To epsilon squared. So something. You're right. Sorry. Yeah. I want to write it as I wrote it there. One. Yes. Sorry. I just wanted to write it. So this is p, and the construction is of size p to the power 5. So this is exactly what we wanted to achieve. And now I want to say why we have this requirement. So for Bézout's theorem to hold, we use the fact that D is at most P. Because otherwise, G may contain Q as a factor in it. So here we use D is at most P. And in this language, it tells us that n to the 1/2 is at most n to the 1 over 4 over epsilon to the 1/2, which tells us that epsilon is that epsilon should be small.
From what I remember from this paper, is they use the algebraic geometry codes in a setting that's considered non-standard. So they choose the curve and everything from in a different setting that is used to get good codes. So is it?
Okay. I'll try to make some.
But you just note that the field size here depends on n, where in standard algebraic geometric codes, the code size does not, the field size does not depend on n. In this way, it's non-standard.
In usual, this is what they want to. You want to make the field as small as possible. So the construction is sort of clear. And now I'll try to explain something about what's the EVESC and about how this comes from algebraic geometric codes. I'm not sure that I can do a good job. Yeah, I think we will finish earlier than usual. So, a few words about this. So again, how does the coding theory thing work usually? We take f, some polynomial. This will be the message. And we will encode it by evaluating it at some points. So encoding f of p1, f of p2, f of pn. This will be our encoding. And the property...
What are p1, p2?
So the p1, yeah, it will be some points in some field or yeah. So this is the general framework we usually do. And the Reed-Solomon and Reed-Miller take this to be polynomial of a certain degree and take this to be a large enough set so that we can interpolate, so that we can recover f, and then we have some codes. And so the sort of the property we want such a thing to be is that if f is non-zero, then the probability over I from 1 to n of f of pi is 0 is at most epsilon. This is a sort of condition we want to have. And this will be 1 minus the distance. And what Gopa suggested, and then later, I'm not sure how to say these words. So there is a, do you know, Sfafsman, I don't, so there are many people worked, and I'm sorry that I don't know. But this is a huge field, algebraic-geometric codes. There are many works on this. And what they say is that we choose f in some, so we first, so it's not, okay, we choose some points in some field or on a variety, and these points have information about some polynomials. In some, what I'm saying is not accurate, but these have information about some polynomials, and we choose f to be one of these polynomials.
You call everything p, the points, the polynomials.
No. So,
No, but even in just this section.
Where is it? No, here p are points.
So one of the polynomials.
P1 contain information about. On. So this is the general idea. And what they do specifically, so in this type of upper bounds, we usually use, how is it called? No, here we will use Riemann Roch. In here we use Schwarz-Zippel. So here we use usually, so the simplest Reed-Muller, Reed-Solomon is like simple properties of polynomials. And Gopa said that, suggested that the way we interpret this sentence is to use Riemann-Roch theorem, which can be thought of as saying that the only polynomial with many zeros at some points is 0. This is a rough statement, which is sort of similar to Schwarz-Zippel, but has a different flavor. Like it applies in different. So I will try to give some intuition, although I'm really not an expert on this. So if any of you have better ideas. So what sort of Riemann-Roch tells that if we choose a variety to be some variety of Q, and let's say Q is irreducible, or this variety is smooth, or some different conditions, then this variety has some topological property. So this variety has a genus which tells us that it's not.
How many variables do we have? 2 variables?
So yeah, we can think of a number of variables as 2, but this is a general. I'm not being very specific, so you can think about higher dimensional objects as well. In general, every variety has a genus which is some number, and it tells us how crazy is this variety. So this is how I think of it, but I don't have a very good intuition. So if
the only genus 0 is the straight line, and then
yes. So and then if we somehow manage to choose a variety of low genus, so it's not very crazy, but has many points, then this will give us a good way to encode things, because these points will give us, will tell us that the polynomial will give us a lot of information on this polynomial, because the variety is controllable in some way. And I can try to make it more formal, although I'm not sure that I can, but let's see what happens. Okay. So the basic, we associate with every variety some vector of integers, and this vector is called a divisor. So in our case, usually, so we have some irreducible variety, and we can define a divisor for this variety. And now it depends on the exact scenario, so I will not be very formal, but it will be roughly sum over some points, some integer times the point, and the sum is just meaningless. It's a free abelian group. So these are just coordinates. The p are just coordinates in the vector. So for every variety, we can define this vector, and this is called the divisor. This I think the standard divisor. There is also the divisor at infinity, but so so this just associates some vector with a variety. And intuitively, I think this number tells us how many zeros the polynomial defining this variety has at the point p. So this can be a negative number, then the function has a pole there. But so I'm not being very accurate, but we can assign a divisor to any variety. And so there are two, so there is one, so this is a divisor, I think is usually denoted by G for some reason, I think. And we can define a vector space associated with a variety or with a divisor to be all the x's, and I will not, so, okay, all the x's, so that x is at least g, and this means coordinate was. Including 0. So with every variety or every irreducible polynomial, we can associate a space of polynomials. Of rational functions, actually, but I don't want to make it very accurate. No. So this is called the Raymond-Roth space, I think. And again, intuitively, this tells us how many zeros we have at every point. So these polynomials must have at least as many zeros.
It's a subspace?
It's a subspace of polynomials, yes. It's a subspace of rational functions on the variety, but I don't, let's, yeah. And and there are so every divisor has a dimension of G, which is a dimension of LG. And we can also define the degree of to be the sum of these numbers. And here there is some. Never mind. So there may be also the degree of P, but it's in our scenario, this is the degree of G, which didn't define exactly. And what one property is that if the degree of a polynomial is, or if the degree of a divisor is smaller than 0, then the dimension is 0. So there are no polynomials that are, there are no rational functions that are bigger than something that has only, that has only poles in it, or something like this. And the Raymond-Roth theorem, which I'm not sure, I don't think I wrote it. No, I didn't write it. The Raymond-Roth theorem tells us that if the degree of this is not smaller than 0, is bigger than the genus, or like two times the genus minus 1 or something. So if the degree and we choose then every, I'm not sure that I can give into, no. I will not write anything formal. The Raymond-Roth theorem tells us that this genus, this natural number gives us a way to control the behavior. So specifically, I don't know how to write this formally, but if we choose, if H is a divisor with disjoint support from G, so we choose these endpoints in a variety, and we choose some divisor whose support is not in these points. And then the good polynomials, so L of H, G, P1 to Pn, contain information about this. So we can encode polynomials here by evaluating at all these points. And we want this, so what we want now is to have the dimension of this as large as possible. So then we can contain a lot of information about many polynomials. So this is the the high outline, and then you need to find points on a variety with a small genus, and to define an H so that L of H has a large dimension, and then you get good codes. I hope I was clear in any way. I'm not sure that I was, but do you have any questions?
What do you mean contain information?
So if we evaluate a polynomial here on all of these points, then we know the polynomial. So if we know all of this, then we know the polynomial.
So it's just an interpolation.
I think that it's. I think that recovering is a totally different question. I'm not sure what you mean by interpolating, but it's not. It determines, but actually getting to it is. I think it's complicated. I tried.